Good evening or good morning or afternoon, depending on where you are in the world. Welcome to the CWNP webinar on common Wi-Fi problems. Now, I want to start out right here at the beginning and let you know that we will have an additional webinar with a similar title coming up in the first quarter of next year. You'll see that announced in our newsletter. But when we do that webinar, we'll be covering 5 additional common Wi-Fi problems. Today we're looking at really the 5 most common Wi-Fi problems that are experienced. My name's Tom Carpenter and I'm the CTO here at CWNP, and we're going to be really focusing on some valuable information for the real world and also useful information for the CWNA and the CWAP exams. If you're studying for those, this information will be helpful for you there, and in fact helpful for practically all of the exams in some ways, but we want to keep the information very practical as well. So we're going to jump right into the content today. If you have questions during the webinar, please feel free to chat those in either in the Q&A window, or you can simply use chat and send them to all participants so that everybody can see them as well. So either way, you can send in your questions and I'll make sure I get those to you. So let's just jump right in. And the first thing I'd like to do is make sure that everybody on with us here understands the certification offerings of CWNP. We have a path that many people choose to go through that leads ultimately to the Certified Wireless Network Expert. And along the journey, you study the foundations of Wi-Fi, so you understand RF fundamentals and Wi-Fi fundamentals. That's in CWNA. And then in CWSP, you study security specifically. In CWDP, you study design specifically. And in CWAP, you study analysis or troubleshooting specifically. So we really focus on those 3 core skills at the professional level: security, design, and analysis. And then for those that pass the CWNA exam, as well as all 3 professional level exams, they have the opportunity to apply for the CWNE certification status. There's no additional exam for CWNE, but the previous 4 are required. And what you'll do is submit an application that will go before the Board of Advisors to determine whether or not you meet the requirements of the certification, which is that you pass the 4 exams, but also that you have 3 years of documented enterprise Wi-Fi experience, that you have the ability to communicate Wi-Fi, that you can help other people understand it. For example, you may have created some videos, you may have created documentation of some sort, you may publish a blog, write a book, anything like that would qualify. And for more information on any of our certifications, make sure you visit cwnp.com. And for information on the CWNE application process, for those of you that might be interested in that, watch for a video that will be released on our YouTube channel as well as at the website in the coming couple of weeks. And our YouTube channel is CWNP TV. And I just point that out because if you go to YouTube, search for CWNP TV, you'll see archives of past webinars and other videos. This webinar will be available by tomorrow, and so you'll be able to watch that. And just a point, if you're with us and you were unable to be on the webinar earlier today at 1 p.m. Eastern Standard Time, we apologize for that. There were some technical difficulties, literally no internet available for the presenter, aka me, and I was unable to do that presentation at that time. But this is the same presentation, and it will be recorded and placed on YouTube for those that don't want to attend something at 9 p.m. if they happen to live on the East Coast of the United States. So that's information about our certifications. Watch for that. Also, watch for announcements about our conferences next year. We will be doing a conference in Prague in June, and we'll be doing a conference in New Orleans in September. So exciting things happening there. So let's get right into our agenda for today. Now, what I've done is I've broken these 5 common problems into 2 categories: performance problems and connection problems. So obviously we have to have a connection to use Wi-Fi, and once we're connected, we want it to perform well. Well, there are 3 common performance problems that we'll talk about, and 3 common connection problems that we'll talk about. So the 2 common connection problems. The 3 common performance problems are interference, congestion, and low data rates. And the 2 connection problems we'll talk about are the inability to connect to Wi-Fi, so you can't connect to the Wi-Fi, and the inability to connect to network resources. So maybe you have a Wi-Fi connection down in your little task tray in Windows, you know, it says you're connected, and yet you can't use anything. So these are 5 common problems that our Wi-Fi users face. And yes, I'll tell you right now, that the cannot connect to network resources is usually not a Wi-Fi problem. All the rest of these we'll talk about are actually Wi-Fi problems. When we talk about common problems again in the first quarter of next year, we'll address 5 additional problems. But these are the 5 we're looking at tonight, and the webinar will run about 30 minutes or so. So the first common Wi-Fi problem then in the performance category is interference. Now, the reality is that this can also be a connection category problem because it can prevent you from connecting, but we'll talk about that more later. Interference is really just anything that corrupts or modifies the original RF signal. So a signal is sent in such a way that there is data modulated onto it. Okay, so we modulate digital data onto our radio frequency signals or waves. And it's a signal because there's something modulated onto it, right? Otherwise, it's just RF energy. So, for example, our electric motor here in the lower right of the screen may indeed generate RF energy, but that's not a signal. That's just RF energy. It's an RF wave. So there's a wave there, but there's no signal. A signal is a modulated radio frequency wave, and the reality is that interference can cause it to be such that we can't process that wave appropriately. And when we can't process it appropriately, we don't see the signal there. There's not meaningful information there for the receiver anymore. And so there are lots of things that can cause interference. We can have interference from really anything that generates RF energy in the same frequency space in which we're communicating. So for example, it could be a non-Wi-Fi transmitter, something like a microwave oven, or a electric motor, or it could just be an incidental transmitter or an unintentional transmitter. So when I say non-Wi-Fi transmitters, don't think of just the devices that use the same frequency space, but they're not 802.11, but think of things like a microwave oven. You know, it's not really generating a signal. It's not trying to communicate anything to the food, is it? That would be interesting if it was. So it's not trying to tell the food something. It's just generating RF energy. And that RF energy is going to be absorbed by the food, and that converts the RF energy to heat. So when RF energy is absorbed, it's converted to heat, and that's what heats up our food. So microwave ovens generate 2.4 gigahertz frequency waves, and they can interfere with Wi-Fi in that range. Electric motors could potentially generate unintentionally RF energy, as well as other devices. And then you have non-Wi-Fi transmitters that are intentionally transmitting a signal. And a good example I like to give a lot is I've got these two devices. One connects to a projector, for example, or a monitor or something like that, and the other connects to a computer. And it sends an HDMI signal across 5 gigahertz. So it uses usually the upper channels, what we've often called Uni 3, but who cares about that? The upper channels in 5 gigahertz that Wi-Fi uses. So we won't worry about saying Uni 3, we'll just say the upper channels, 165 and up in that area. So it uses those channels and it does 100% utilization. So when those two devices are sending the HDMI data between them, so that the projector can display it or the monitor can display it, and it's wireless, it is transmitting that at such a rate that it completely utilizes that channel. And you're not going to get anything Wi-Fi to work in the same channel. Now the device does try to play nice, but it has to use one I've found of 3 different channels up there in the upper channels. And the point then is that if you're using all 3 of those channels, it's going to interfere with one of those access points. So that's a non-Wi-Fi transmitter. Video cameras could be those as well. Additionally, other wireless networks can cause interference. We can have co-channel and adjacent channel interference. So co-channel interference is when 2 802.11 devices are in different basic service sets or maybe even ad hoc networks, and they are on the same channel, even though they're in different basic service sets or independent basic service sets. And then adjacent channel interference is when a channel that is different but overlaps or doesn't technically overlap and it still causes interference. So for example, 2 5 gigahertz channels side by side can still cause adjacent channel interference if one of them is transmitting at too high of an output power, for example. It can cause this problem. But in 2.4 gigahertz, of course, channel 2 would be an adjacent channel that overlaps and causes interference with channel 1. So these are all causes of interference, and it's a common cause of performance problems in a Wi-Fi network. So what are the solutions to interference? Well, first we've got to find it, right? We've got to find the source of interference. We can do that with spectrum analyzers. We can do it with protocol analyzers to a certain extent, in that you can see the signal strength possibly if it is another Wi-Fi network. But if it's not another Wi-Fi network, if it's a non-Wi-Fi interferer like a microwave oven or the video device I was talking about, then we really have to use a spectrum analyzer to locate that. And again, with the spectrum analyzer, you look for the signal to become stronger, or the RF energy to be stronger if it's not actually a modulated signal. Once you find it, a few options. You can remove the offending device. You can change the channel on the AP so that it is using a different channel than the interfering device. So if you can't move the interfering device, let's say it's a motor in a manufacturing environment and it's causing some problems for a laptop near it, well, you might need to change the channel the AP is on that laptop uses so that the laptop can move to that channel and get away from the interference. More common might be something like a microwave oven causing interference. You can also reduce the output power of APs and implement a proper channel plan. Now, this would be the solution for co-channel and adjacent channel interference. So if you're getting a lot of particularly adjacent channel interference, look real close at your APs and your channel plan. If you're getting a lot of co-channel interference, then again, look at your APs, your channel plan, the output power of these APs, and if it's a neighboring network, it could cause a total demand for an internal redesign of your network in order to get the right channels on the perimeter closer to the neighboring network to deal with that. The problem is sometimes the neighboring network is not at an edge, it's above you or below you. Because a lot of times we're in buildings, multi-floor buildings, and our business may be on one floor, and then the floor above is a completely different company, and the floor below is a completely different company. So in that kind of situation, you'll have to try to stagger your APs under those other networks as best as you possibly can and just work with it. This is one of the reasons that we argue so much for trying to get more 5 gigahertz client devices and being able to use more 5 gigahertz APs, simply because there are more channels in 5 gigahertz for us to use. In 2.4 gigahertz, we only have really the 3 non-overlapping channels in most of the parts of the world, and that becomes a big limiting factor for us in dealing with interference. Let's talk about the next problem that impacts performance, and that's congestion. Some people call it CCA congestion, which is co-channel interference. Clear channel assessment. I'm still back on interference. Clear channel assessment congestion. And what that means is that there's a process that 802.11 devices have to go through in order to get access to the wireless network. And that process is, in its most basic form, carrier sense multiple access with collision avoidance. So Wi-Fi is a listen before you talk solution, because the simple fact is that there's no way to really detect a collision and back off and retransmit like we do on Ethernet. And so because of that, we have to instead make some assumptions. For example, if you send a frame and you don't get an acknowledgement back, there's an assumption that there was interference. Now, that's not true for beacon frames, right? A beacon frame is a broadcast frame, and the AP does not need acknowledgments back. Could you imagine if it did and there were 70 clients in the network and all 70 had to send back acknowledgments? That would just be silly. It wouldn't work. So beacon frames don't get an acknowledgement back, but many frames, most frames actually do. And if they don't receive the acknowledgement frame back, the assumption is it wasn't delivered. So the device that sent it will retransmit. And each time it retransmits, it changes the variables in the CSMA-CA process. So I'm not going to go into extensive detail of these variables here. They're documented in CWNA study guides. They're documented again in CWAP in even more detail. They're even referenced in CWDP. So I'm not going to go into heavy detail, but just remember that one key factor in it is CCA, clear channel assessment. And CCA is divided into two things, effectively carrier sense and energy detect. So carrier sense is, I saw a frame, and what is the signal strength of that frame? So if I see an 802.11 frame, even if it's not in my service set, if the signal strength of that frame is at a certain level, I'm not going to try to transmit. So my service set does not bother another service set. So I'm trying to play nice even with other service sets. So really this carrier sense right here would be one of the factors that impacts and causes co-channel interference, right? So I'm seeing another frame on my channel, I'm detecting it, I've got the certain signal strength that I can see there, and because of that I'm not going to transmit. And then there's just energy detect. And this measures just the RF energy. And if it sees RF energy in the frequency above a certain threshold, then it will not transmit. Okay, so now these values can be found in vendor documentation, and we also give some examples of it in our CWDP official study guide. So that's some useful information for you to know. There'll also be information about this in the CWAP study guide, which we'll be releasing next year, and there's information about it in the current CWAP study guide as well from Cybex. So what are some suggested congestion solutions? Well, the big thing is you got to get fewer devices on the channel. It's really that simple. We've got to get fewer devices on the channel to reduce congestion, or get more high data rate devices. So either one of these can be helpful, but we'll talk more about data rates in a moment. So one thing we think about is load balancing, right? Or spreading the load. So what we want is multiple channels in an area so devices can connect to these different APs on these different channels. So instead of having everybody connect to one AP on one channel, we have our devices connect to multiple APs on multiple channels. So the general congestion solution we hear, particularly from vendors, is, hey, implement more APs. And that is part of it, but remember, you get to a point of no return. So you get to a point where you have too many APs, and now your co-channel interference is causing problems where you're not really getting the performance gain that you want. So there's a limit to what just multiple channels within a frequency band can do for you. So the next step would be, as indicated in the box in the lower right corner here, band steering. And this is take advantage not just of multiple channels, but of multiple bands. And so band steering really says, hey, let's try to push the clients over to 5 gigahertz that can use 5 gigahertz. And the way that's done is, I don't know if you've ever noticed this, but if you take a look at the MAC address for your 5 gigahertz radio and your 2.4 gigahertz radio in a device, you'll see they both have the same MAC address. So even though one's 2.4 and one's 5, they're the same MAC. You've probably noticed you can only use either the 5 gigahertz or the 2.4 gigahertz radio at a time in your client device, right? So you can either connect to a 5 gigahertz SSID or a 2.4 gigahertz SSID. You can't do both at the same time. And there's one MAC address. So some APs will remember that a client has connected on 5 gigahertz before, and since it has, they know when they see that MAC address, it has a 5 gigahertz radio. So it'll just ignore the 2.4 gigahertz, forcing it to go to 5 gigahertz. Others, if they've not heard from the device before, they may delay responding to a 2.4 gigahertz request, hoping that the client will try 5 gigahertz with the same SSID and get on. So that's band steering in its basic nutshell. Vendors implement it in slightly different ways, but that's the basic functionality of band steering. You can also do some manual band steering, if you will, in your configuration process. So if you have some type of wireless client security tool that runs on the client, and you can configure profiles in advance, and the laptop has a 5 gigahertz radio, and you know 5 gigahertz is everywhere in your facility where your SSIDs would be, then you can simply only configure the 5 gigahertz SSID in their profile so that they can only connect to 5 gigahertz. And that would push those clients over to 5 gigahertz, which can really help with congestion because, once again, you can have more 5 gigahertz APs in a space than you can 2.4 gigahertz APs simply because you have more channels. Now that's, of course, assuming you stick with a 20 or 40 megahertz channel width and you don't use 80 megahertz channels in 802.11ac or something like that, which would use up more of those channels. Now, the next problem we'll talk about is low data rates. Low data rates cause problems. Well, they cause problems with congestion because it takes longer to send a frame, right? So even with fewer devices, it's about utilization of the airtime. And so if you've got a bunch of devices connected to a service set at 1 megabit per second, and those devices need to transmit 100 megabytes of data, and then you've also got some 802.11n, maybe let's say 150 megabit data rate clients, even though they're that fast, they're going to get throughput that's very low because they're continually having to wait on the frame transmissions of those 1 megabit per second clients. So they're dragging down the network. Now, these 1 megabits per second clients may be connecting to an AP and sticking with it when they should roam to another AP because there's a better AP nearby. And so one of the things we can do to kind of force these low data rates to go away from our network is simply disable them. So in your APs or your wireless LAN controllers, you can go in and you can disable low data rates so that your basic rates do not include them, and your supported rates, and they're not included anywhere. They simply cannot use, say, 1, 2, 5.5, and 11 megabits per second, and maybe 6 and 12 megabits per second. So you can disable these lower data rates. And then once you've disabled them, it effectively means they're going to have to find an SSID with sufficient signal strength so that they can communicate at the data rate they desire, or that you desire, I should say. And what that does is it reduces congestion, because frames, when they're transmitted, go through faster, right? So if everybody is at some data rate higher than 12 megabits per second, then each frame that's transmitted is going to go through faster, which reduces the airtime utilized, which therefore reduces congestion. So that's kind of the theory behind disabling low data rates. There are some contention issues going on out in the community about low data rates right now, but the general perception and what we've seen in implemented networks is that by disabling the lower data rates, you can reduce congestion in the network, though you could potentially introduce some dead spots for some clients in some cases. So that's something to keep in mind. Now, know that your data rate is a factor of two things, really. The data rate that you get is a factor of receive sensitivity, and we have an example chart here. So the chart here says at negative 90 dBm, you can do MCS 0, at negative 91, 6 megabits per second. Well, technically speaking, the data rate you get is going to be based on the signal to noise ratio. So even though we have this receive sensitivity, these receive sensitivity ratings, it's best to think of them as being related to an assumed noise floor. And generally we can trust that noise floor assumption, or at least pretty close to it, within a dB or so. But if the noise floor for some reason is oddly high in an environment, then these receive sensitivity ratings aren't going to be as accurate, because the data rate you can get is about, can I distinguish the modulated data from the noise in the environment? So think of it like this. You may have music playing, and you can hear it nice, you can tell all of the words that they're singing, you can see it clearly, hear it clearly, and then somebody starts making noise nearby you, like maybe a jackhammer outside your door, and the music's still playing at the exact same decibel level that it was before, right? But you've got something at a higher decibel level that's making it so at your ears, those two noises come to you, those two sounds come to you, and you can no longer maybe make out the words of the song. Even though you can tell there's music there, you can't actually make out the words. What that means is you have lost your ability to demodulate that sound wave that's coming from the music because of another sound wave that is too strong nearby. So your signal, the music, to noise, the jackhammer ratio, is not good enough. And that jackhammer, if it was a little quieter, you could probably still distinguish the words. It might not be a pleasant experience, but you could still distinguish the words, okay? So signal to noise ratio is an important thing, and we usually measure that in decibels, things like 20 decibels, 25. So we often say if you've got 25 dB SNR, you'll probably get a really good data rate. But if you have 1 dB, 2 dB SNR, you're going to have the lowest of data rates, or simply not be able to connect depending on the scenario. So what are some low data rate solutions? Well, one thing I've already mentioned earlier, and that's disable lower data rates. So if you're having problems with low data rates, it could be that you've got, again, the sticky client phenomenon, and disable lower data rates, and you can force them to roam to another AP because it won't let them do dynamic rate shifting, right? Backing off the data rate. It won't let them do that down to those lower data rate levels. You can also install more access points, and at the same time as disabling lower data rates. So here's the thing to be careful about. If you have an existing network right now and you have not disabled lower data rates, and then you just go in and disable them, you may have holes all over your network. I should say more specifically, holes all over your facility, because there's really not a physical hole in your network, is there? There's a hole in your facility. There's a place, a physical square footage area where you don't have a signal with sufficient strength above the noise floor, SNR, in order to be able to have the data rates that are allowed. And so when you disable lower data rates, you may have to install more APs to provide client connections. You can install more APs, you can configure the clients. And so some clients do give you the ability to change things like roaming thresholds and that kind of thing. In rare occasions, you can even change the data rates the client supports. But the point is, you may be able to go in and configure your client devices, if you own them, to help with the low data rate solution as well. And I should stop right here before we move on to talk about a couple of other common problems and point out that I'm just giving you some of the solutions to these problems, and I'm just dealing with some of the things that cause these problems, just to introduce you to these concepts, to make sure that you're thinking about them and you understand them for both design and for analysis or troubleshooting of your wireless networks. All right, so now let's talk about the connection problems. And the first one we'll talk about is I can't connect to Wi-Fi. You get this all the time, right? But I will tell you this, a lot of times I can't connect to Wi-Fi is really I can't connect to network resources. Wi-Fi is working just fine. So we'll talk about cannot connect to network resources next. But first, there are some things that keep you from connecting to Wi-Fi. You try to get your Wi-Fi connection, maybe it just hangs or something like that. Realize that the beacon frame is always transmitted at the lowest data rate, and the client might be able to process the beacon frame, but it may simply not be able to communicate with that AP effectively enough to get on the network. So it can see the SSID, but when you try to connect, you can't. So that would be an interference problem or an insufficient signal strength problem, you might say. And the solution obviously is solve your interference or signal strength problem in order to get the connection there. It could be a misconfiguration, and then you just want to configure the client or AP appropriately. So there may be some configuration setting on the client that's preventing it from working. Let me give you an example of that. You may have found this. I've run into this a couple of times with dual band client adapters in computers, and had this adapter. I've had several like this now, but one particular one was, I wish I could remember, I believe it was an Edimax, but at any rate, I had this particular adapter, and it was a dual band adapter, but every time I plugged it into Windows 7, and I believe it was even Windows 8, it only worked on 2.4 gigahertz. And I was using the vendor drivers from the website. And there was, even though you'd go into Device Manager and you'd see 5 gigahertz in there, it would never see the 5 gigahertz wireless network that was definitely there. It didn't even see it, didn't show it at all. It only saw and connected to 2.4 gigahertz. I actually found a third-party driver for the device, installed that driver, and then, wow, magically 2.4 and 5 gigahertz worked. So the vendor's driver didn't work, but some other driver, because they used the same chipset that someone else was using, and I used that other vendor's driver, and guess what? It worked perfectly fine. So that's an example of a configuration problem. It's not really a firmware problem, because this is a device driver. So these are the kind of things you can run into. It could be security settings. So obviously you're not going to be able to get on if you're using passphrase security with WPA2 if your passphrase is incorrect, for example, or if EAP is configured appropriately. And then it could be a firmware problem. So you may remember sometime back Cisco had an issue when Microsoft implemented 802.11w management frame protection in Windows, and then all of a sudden those devices couldn't connect to some Cisco APs. And it was a problem in Cisco's APs, not with Microsoft's implementation of 802.11w, and Cisco had to implement a firmware update. And so the solution there is to update the firmware. So these are just some common causes of not being able to connect to Wi-Fi and some basic solutions to them. We can get into some very advanced discussions of this, and we do that in our CWDP and CWAP training courses as well as the study guides. Now let's talk about cannot connect to network resources. This is actually my favorite topic because I have found that most of the time when you've had a stable wireless network that's been working, and all of a sudden a few users cannot connect to Wi-Fi, and if you could see me, I've got air quotes going here, they cannot, quote, connect to Wi-Fi, unquote. The truth is when you get to their computer and you're doing your own problem analysis, remember good troubleshooting, gather information, verify the problem, right? Don't trust the user's words. Just because they say they can't connect to Wi-Fi doesn't mean it's true. So a lot of times the real problem is not Wi-Fi at all, and Wi-Fi is still fine. It's that they can't connect to network resources even though they're on Wi-Fi. So some common causes, DHCP cannot be reached. So something has happened within the network infrastructure to where the DHCP server can't be reached to give out IP addresses. So we can ensure DHCP relay is enabled or implement DHCP per segment. You know, if you're using Cisco routers, for example, each segment that connects to the router can have DHCP running for it in the router rather than having a centralized Windows-based DHCP server or something like that. If you're using some type of centralized Windows or appliance-based DHCP server, then you'll need the routers to relay DHCP to those servers. A second problem that's very common that we see is DHCP pool depletion. So the DHCP server just has no more IP addresses to give out. Now it can reach it, but it can't give them out. So in that case, we need to implement more DHCP pools or larger pools. It could be an infrastructure configuration error. In that case, you want to configure the routers and switches appropriately. So for example, you may be on a router doing some type of round robin forwarding where the first request for a certain service goes to out one interface, and the next request for that service goes out another to give kind of some load balancing to those service requests, maybe to different servers. And if that's the case, you may be forwarding out one router interface to a switch that's broken. There's something wrong on the switch, right? So it can't get to the destination server anymore. So half of the clients or so are not functioning because they can't get through. In that case, we need to configure routers and switches appropriately or repair the problem. And it could be that the network's working fine. They're just trying to get on Facebook, okay? So in that case, it's an internet connection error, so we need to go to the internet connection, find out what's going on there. Maybe it has nothing to do with the internet. Maybe for some reason those clients are getting their DNS configuration wrong. So check the DHCP pool settings. If DNS is configured statically, check that. Make sure the DNS server is configured appropriately. Again, I want to emphasize that if you've had a stable wireless network that has been working fine, and now all of a sudden users are calling and saying, I can't connect to Wi-Fi. Sure, verify wireless is working if you can do it without going to the location, meaning you've got centralized management or something, RF monitoring, you can see it's there and everything seems okay. You might even try resetting the AP. If it's still not working and you've done that from remote, it might be time to look at one of those client computers and find out, is it really Wi-Fi or is it really something on the network side that is broken in your particular scenario? Well, that's all we have scheduled and planned to cover. So what I'd like to do is give you just a few minutes to ask any questions that you might have about the presentation here today. If you have questions, again, you can chat them in the chat box, or you can send them in the Q&A box. Either way, if you chat them in, go ahead and send them to all participants. And I'll just give you a few minutes to ask any questions, and I'll do my best to answer them. Do remember that this webinar is being recorded and will be, by tomorrow, up for you on YouTube so that you can watch it again. Share it with your friends. We would ask you to do that. If there's people that you think might be interested in this or other webinars, let them know about our CWNP TV channel because it's a great source of technical information for people interested in Wi-Fi. So I'll just pause and give you a few moments to come up with any questions you might have. And if there aren't any questions in a minute or so, we'll go ahead and end the presentation. For those that aren't interested in Q&A, thank you very much for joining us on this webinar. And feel free to take advantage of our forums at the website. If you have questions on an ongoing basis, there's a great community out there that answers questions and helps support folks interested in Wi-Fi. And make sure you explore our certifications in more detail. If you do have to go, thank you for attending. Okay, we've got a question here that says, if there is a channel change on an AP due to DFS, is there a way to know the source of DFS? That's a really good question. DFS is dynamic frequency selection, and it's a required feature in most regulatory domains in order to keep your wireless network in 5 gigahertz from interfering with radar. This is particularly important around airports and things like that. And so the question is, since all APs have to do this DFS monitoring if they're using DFS channels, and there are specific channels that is, then if they detect DFS, they have to switch channels. So here's the question. Is there a way to know the source of the DFS? No, not really. The AP, most modern APs, at least at the enterprise level, will log the channel that they detected radar on and the time that they moved away from it. But they're not really going to be able to tell you specifically what that was because they're not going to demodulate the radar per se and then tell you some kind of a vendor ID or something like that. So there's no real way to know the source of DFS, but chances are if you're getting that kind of radar interference on a channel, then you will understand that you're in an area where there's something that would cause that. You're near an airport, maybe it's a smaller airport or a large airport, something of that sort. And so that's generally when you're going to see it. But there's not really a way to know for sure the source, only to know that that particular channel is experiencing DFS events. And so you'd certainly want to go in and then disable that channel so your APs with something like radio resource management or something do not bounce back to it because you don't want those switches away from it again and again. Okay? Any other questions? All right, if there are no other questions, again, thank you very much for attending. Good luck with any of your CWNP certification studies you're performing right now, and I hope to see you again on a webinar in the future. We do these once a month, usually on the third Thursday of the month, and we do one at 1 p.m. and one at 9 p.m. of the same webinar in most cases. So look forward to those. If you're not subscribed to our email newsletter, go do that at the website, and then you'll be notified of these webinars when they happen.